Before we go any further, let's talk about some real basics. How do computers make sound? Now, you probably have at least an intuitive idea about how this works, and if you're an electrical engineer, then maybe you've studied this formally. But we're going to go over fundamentals right now, and later in the course we'll come back and look at things a lot more carefully. But for now, what I want to do is explain what is sound, talk about what does analog mean, and talk about digital audio representation, and then how do we get from analog to this digital representation, and how do we get from the digital representation back into analog. And finally, we'll very briefly look at the idea of actually computing digital representation of sound that can then be turned into analog and played. So to start with, what is sound? Sound is just variation in pressure. Pressure variations travel through the air as waves, and we call that sound. Sound travels about 1,000 feet per second. We have a unit called Hertz, which is named after Heinrich Hertz. You can see his picture in the corner of the slide here. He was a pretty amazing man who discovered or who proved the existence of electromagnetic waves and worked in the late 19th century. So that's where this thing Hertz comes from. It really just means cycles per second. We can hear variations in pressure, or in other words, sound, when the rate of vibration is between around 20 hertz, or 20 cycles per second, up to about 20,000 cycles per second. And we can hear amplitude variations over 5 orders of magnitude, from the threshold of hearing, the quietest sound you can hear, up to the level of pain. So what does analog mean? Pressure variations in sound can be expressed or represented in many forms. We could talk about mechanical displacement. So for example, if you were talking into a microphone, there's a diaphragm on the microphone that is vibrating in and out. That's mechanical displacement. We can have voltage variations. That's what comes out of the end of the microphone. We can represent sound or vibrations as wiggles in a vinyl record groove. I always wonder whether I need to explain what a vinyl record is to people, but they're coming back. You could talk about the degree of magnetization on tape, or optical density in film, which is how sound used to be recorded in movies. And all of these representations are called analog because somehow there's some property that varies in proportion to air pressure, or analogously to air pressure. Digital audio representation is different. So here's how we get from a continuous analog representation to a digital representation. First of all, we measure the continuous analog signal periodically. So here we see at discrete periods of time, equally spaced, we take a measurement. That's the little dots along the curve. And we store these measurements as a sequence of numbers. Pretty simple. When we want to convert from digital to analog, we use the sequence of numbers to control or produce a voltage that changes as the numbers change. And then we filter that voltage to produce a smooth signal. And here's an example of not recording sound and playing it back, but actually generating sound from nothing but a program. This is a classic algorithm for called a wavetable oscillator that produces a periodic variation in sound, or the representation of that sound. And here's how it works. We have a table that's shown in the lower left of the diagram. The table is just an array of numbers. And what we want to do is move through that table over time and index into the table to retrieve a number which represents the instantaneous amplitude. And then we can scale that by an overall amplitude control and output the sound. Now, one trick here is that if we just consecutively output each element of the array, then we would generate a fixed frequency, a fixed period. But usually in synthesis, we want to be able to control frequency. And so to do that, for each sample we output, we increment a variable called phase by some increment, which is the frequency control. And the phase is the index into the table. So the faster phase increases, the faster we go through the table, and the higher the frequency that we get. When we hit the end of the table, we wrap around, and that's about it. So that's the basics of a table lookup oscillator. So let's move on.